Okay. Anyway, hope everything's doing well. um, what we're doing right now, we have a very small window here because I'd like to get you just a couple more grades before the end of the quarter. And so one of them will be this homework assignment, and I think it's worth 10 and 15 both, so it's like 25 total. And then we're going to talk about scientific graphing again today, and we're going to kind of finish this packet. And then tomorrow I'm going to talk about the design of experiments and how, if you were to do your own experiment, what kind of things would you have to look for? How do you decide where the independent variable was? And then the last grade I'll have is I'll give you a little quiz on Thursday, and I'll even tell you what it looks like. I'm going to get an experiment that somebody did, and you'll have a data table. And I'll go over all this today, okay, again. And you have to decide which one was the independent variable, what was the dependent variable, set up the graph, draw the graph, spread out, scale the axes, plot the points. We're going to do all that today. You're going to do it again for homework. We're going to talk about it. And then you're going to try to interpret it. Like, how do you interpret it like that? So my point today is not to show you what kind of things are the same in math, because a lot of the stuff in graphing is the same, but I'm trying to point out things that are different in a scientific graph than they would in math class. So be careful about thinking, hey, I already know how to graph, nothing you're going to teach me. And I agree that your class, having been in stats, you actually are way ahead of the other class. So I'll try to go as fast as I can, but you guys are actually more capable of understanding this at a faster rate. Matter of fact, you even had a lot of the stuff I'm going to do today, okay? Can you what now?
Can we get bonus points for it?
I guess I thought you didn't like bonus points, sir.
Oh, not like curves.
Oh, you like curve?
Yeah.
Oh, okay.
I like sharing it instead of just giving it to the person who doesn't need it.
Like,
I like
kind of like socialism, like.
Well, you know.
Yeah.
I mean, sure. If you want to phrase it like that.
I love that.
Okay, all right, that's good. So, and you don't want too many people to have too many points, do you?
No.
I mean,
Fine with that.
so, wait, it is okay?
Curve.
Your group is like Amazon.
So, okay,
I mean, you were the capitalist. That's great. So.
okay.
You want about 1%. You have all
I think we have a combination here, and I'm gonna stop talking about that because it's on tape and all that. All right, so let's go back to our lesson, and what we have here is when you do your experiments in here, I would like you to make your own data tables. Okay, instead of me giving them to you, I want you to be able to make your own data tables. So what I'm looking for is that you have in the header, this is called the header, that you have a label and you have a unit. Everybody got that? And then, okay. Oh, wow. As a matter of fact, I happen to know that this is magnified way too high. There we go. Okay. Here we go. All right, now we're ready. Anyway, so when you do your own experiments here, I want you to be able to make your own data tables, because I think that eventually when you do take the ACT, and I don't know how things are going to go there. I think it's a really weird year. I know my niece is applying to colleges. She's already gotten into some, but most of them are waiving testing things this year. But I don't know what's going to happen. Is that going to crank back up? Are they going to have testing again? What now? Yeah, like standardized testing. Yeah. So anyway, when you do take things like the ACT, and people say, well, how do I get better? The science section of ACT is always my worst one. And some of the things here are actually what they're looking for. For example, when you look at of the 7 different sections on the ACT, 5 of them are quantitative. They either have a table or a graph, and they want you to look at numbers, and they want you to maybe look at a data table. And I'll tell you right now, the faster you can figure out who the independent variable is and the dependent variable, you can get a picture of what this person was doing. Now, look at this right here. What we see is these two things. And I can't remember how far we got. We didn't get too far yesterday, did we? I think you talked a lot about MLK. Well, anyway, let's take a look at the experiment. Here's something that's different. If I were in math class, most data tables look kind of like this, don't they? And I know why math people do that, because when they have a coordinate on a graph, they always put X and then Y. And so when they made their little mini data table, they always put X on the left and Y on the right. Well, that's not necessarily the case in science. This is your experiment, right? It's your experiment. And you can decide where you want to put the data table. But in this case, which one is going to be the X and which one is going to be the Y? How do we know? What do you think?
Probably the volume's going to be the X because it says in the experiment, in the above experiment, carefully measure volumes of liquid were taken to balance and mass out. So they did the volume first, so the volume correlates to mass.
Okay, so if I were there watching you do it, I would know which one was the independent variable. But if I'm not there, I have to get some clues from you. And that's a nice clue right there. So whether it's ACT or whether it's this experiment here, I have to see myself, what do they do? I see a picture right now. They had a graduated cylinder, and they were putting liquid in there, and they made sure it was exactly 3 milliliters. Then they took it over to the balance, found the mass of it, subtracted the mass of the container, and then they knew the mass, didn't they? I have an idea of what they did. So when I go down here and ask you about which one is the independent variable, which one is going to be the independent variable?
Volume.
Okay, in this case, it's this one, right? And that's the one that you manipulated. Unfortunately, some science books, and I don't like this, I think it's wrong for them to do it, they'll say, which variable did you control? And I do not say that at all. I say, which one did you manipulate? You caused that 3 to happen, didn't you? You made that 3 come up. You could have picked any number you wanted for the volume, and you picked 3 independent of anything else. So that's called you manipulated the variable. And in almost every case, the independent variable is going to go on the x-axis. So in this case, volume will go here, and that's the opposite of what they might do in math. So I had to figure that out. So whether it's ACT or whatever, you have to figure out what the independent variable was. That means mass is going to be over here, and that's called the dependent variable. Now, since you're in stats, I don't ever use that word, but I think you guys call this the what is it? What? Explanatory. The explanatory variable. I never use that term. Do they ever use manipulated variable in your class? They always use explanatory. Okay, it's just one of those things. I've never used that term, but this is called the independent variable or the manipulated variable. And then this one, because I chose 3.0, the number I get here depended on that. If I had chosen 3.5, I would not have gotten this. So this is the dependent variable, and you call that responding variable, and that makes sense to me. If I do this, you respond by being this number. If I do this, you respond by being this number. And so you call it the responding variable, which is also the dependent variable. All right, questions on that? Is that pretty easy? Okay, now the next thing we're going to do, and I'd like to show you how to do it in case you don't have your calculators with you, and then I'm going to have you pick up your calculator and do it the way you do it in stats class, okay? Can we do it once without the calculators, and then we'll do it with the calculators, okay? Because if you, all right, so let's go on. So the hardest thing about graphing, let's flip this over now. Let's say we're going to do a graph, and right now we want to put the independent variable on x-axis, so what's going to go down here? What's going to go down here? And you want to, whenever I grade, and when I grade your graphing skills, this is what I look for. I have my label, and then I have my units. So I need both of those. Everybody see that? Okay, what's going to go over here on the y-axis? Mass in grams. I used to remember a long time ago when I made graphs. I used to always forget to leave room for the numbers. So we got to make sure to leave room for the numbers. Now what we're going to do is the most tedious part of graphing is scaling the axis. Okay, so let's look over here. If this is going to be my x-axis, what numbers do I have to fit in? I have to go up to about 19, around 20, right? So I go down here, and somebody already counted, I counted these for you. This is a 25 by 45 graph. So this is 45 this way. Now, I have a rule, it's just my rule. You should always use at least half of the axis or more. You get that? I could fit in 5, 10, 15, 20. I could be done here, couldn't I? But that'd be bad because I'd lose all my detail. I couldn't get any exactness there, because my graph would all be right in this little piece here. So let's spread this out. What do you want to go by to spread it out? This is the tedious part. What are you going to go by? If we go by ones, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll be done right here. That's not good enough, okay? We want to spread it out more. So what are we going to go by now? What do you go by? What do you think? Everybody in here should know that. What are you going to go by? What do you think? What? 0.5. Let's do that. So another thing I'd like you to do when you do scientific graphs, do not label every line. Do not do that, okay? So we'll do here. Here's 0.1. Here's 1. And then you have 2 and 3 and 4 and about every 5. That's a good number for me. We don't need to label every line. I can find 3, can I? I can find 3.5. Pick a number that's easy. I've seen people do this on graphing, and they do this mathematical thing. Oh, I need every line to be 2.35. That's stupid. If you go every line is 2.35, you're not going to be able to find these numbers very easily, are you? Be nice to yourself. I'll go by 1s. That's easy. You can go by 2s. That's easy. Going by 3s? That's not as easy. 4s? Pretty good. 5s? All right. Let's do that. 5, 6, 7, 8, 9, and 10. There you go. And 11, 12, 13, 14, 15. And then we have 16, 17, 18, 19, and we'll stop here at 20. All right. Another thing in math, this is different than math class. I remember clearly, man, how many times did I do this in my lifetime? Whoop, whoop, do. All right, how many times done that? Huh? A little sketch of graph. Anyway, we're not doing that right now. We're not going to do that because that makes you think that X and Y axis have to have the same scaling, and they don't. So now we'll go over here, and we see that the Y axis is going to go up to around 16. So what do you think? What can we go by now? We need to get at least 16 numbers on there. So what do you think? This is a 25 by 45 graph. And again, I would not get to this point where you take 25 divided by 16. Don't do that. What do you think? Okay, so I think we'll go by 1s, right?
Sure.
And then if I go to 16, I would have used at least half of the axis. So I think that's pretty good. We don't want to lose some of our detail, so that's why we want to spread these out. The next thing is going to be a little different than they do in math class. Not a lot, just a little bit. We're going to plot the points, and so be careful because this is not like the math book. My X is actually over here, isn't it? So it goes 3, 2.1. So what I'd like you to do is I'm going to go to 3, 2.1. Now, what I want you to do is put a tiny dot. You put a little dot, and you put a circle around it. My goal is, even though I'm going to show you all the skills, how to do a graph by hand, my goal is that you eventually will have computers in here, and we have programs already ready for you, and they have graphing programs, great ones. And so eventually you will be using a program to do your graphs for you. Now they're going to ask you questions like this. What is your independent variable? Well, see, now you know. And then they'll say, do you want point protectors? Now that's what these are. Point protectors are, you want to use a little dot because if I spend all this time doing the experiment and I put a big old fat dot in there, that's going to cause error, isn't it? When I try to find the slope of the line, it's going to cause me a lot of error. So I'm going to use a little dot and a little circle. All right, next one. Let's go ahead and plot the points. Next one is 6 and 4.5. 6, 4.5. Little dot, little circle. Those are called point protectors, okay? So I expect you, now the reason I have point protectors is when I draw the line, if it goes over my little dot, I won't even know there's a data point there. And I want to know that there is a data point there. Yes?
Is that kind of similar, like when we're making our own ruler, that we don't want to like make the line super thick?
Right. If you can draw a line thin, if you can draw it thin, you'll probably get a better number. Okay? That's a good question. All right, next number. Go ahead and keep plotting the points. 11, 9.3. I'll see if I can beat you. 11, what did I say? I lost it. 11, 9.3. 11, 9.3. 5, 6, 7. Now, we're actually not trying to, I don't want to erase because I don't want you to put the dot in the wrong place. Okay. 15 and 12.1. Whoops. Okay, 17, 14.2. Nineteen 16. All right, I made a mistake. Does everybody plot their points down? So when you eventually get on the computer, they'll ask you things like, do you want to point protectors? And you want to say yes, because I do want to see where the data points are. Now, imagine teaching this to the last class. I only have one person in that last class that's in stats, all right? And so the other class, I'm going to teach something a little different. I asked them if they'd ever even heard the term best fit line or trend line. Have you heard that? Okay, so what we're going to do is, a lot of books call it a best fit line or a line of best fit. Some books call it a trend line. And we're going to do this by hand first. Now, when you get the calculator out, you actually are going to call it a linear regression line, aren't you? Okay, so what we're going to do here is this is going to be called a best fit line. Now, one thing that we have a little conflict is Miss Church, I'm pretty sure that when you guys do, she says, draw a best fit line, I found out a couple of years ago that she means straight line. And is that happening in stats where if she says draw a best fit line, is it always straight?
Well, we deal with linear regression mainly.
Right. If it's linear regression, it is going to be a straight line. But you can actually draw a best fit line that's curved. Okay? But if you call it a linear regression line, then it has to be straight. So let's make sure that's kind of clear. How about that? So even the program you're going to use later on, some of the experiments we do will give you a graph that curves. And it'll actually tell you, say, well, try this function, try this function, this math function, and it can actually draw a best fit line that is curved. It's not a linear regression line. That's for linear relationships. All right, so what I want to do is we're going to draw by hand. I know you think people being in stats is going to think this is like, archaic. But what we're going to do is try to draw it without using the calculator. And so I only had a certain number of transparent rulers. And I know some of you have solid rulers. But if you have a transparent ruler, it works a little better. Here's one right there nobody's using. Okay. Anybody else can use it if you want. Now what I'm going to do is, my point is to try to draw a line that best fits the data. Now, if I had to do this and I didn't have my calculator with me, I didn't have the ability to use statistics, what I'll be looking for is I'd want to minimize the perpendicular distances between the dot and the line. Now, the perpendicular distance, and I'll show you how to do this. So I'm going to draw just sketch a line that's not so good, okay? Let me draw a line that's not so good, and I'm going to draw a real faint. I'll draw a real faint line, and let's analyze this. Would you say that I am being truthful with that line, or am I being biased? And you say, well, how do you know? Well, take a look at the perpendicular distance between here and there. That's this much below, and then I have this much above, above. If I were to take the sum of the perpendicular distances above the line, would that equal the sum of the perpendiculars below? And it wouldn't. So I think this is a biased line. Go ahead.
What do you mean by perpendicular?
Okay, way back in algebra 2 probably. If somebody said, find the distance between a point and a line. Remember that? Do you know what kind of distance they were talking about? I'll show you right now. See this? You mean like this distance over here? No. Whenever they said, find the distance between a point and a line, it was always what? It was the...
minimize the residuals.
I think I was pointing the wrong way. Yeah. It's always the perpendicular distance. See that? Now, if I look at this line out here, I can see that the sum of the perpendicular distances above the line are much bigger than that. So that's kind of a biased line, isn't it? So what I'm going to do is I'm going to kind of move the line a little bit. I'll draw a little bit darker. So go ahead, you do the same thing and see if you can sketch it to begin with, and then see if you can come up with one that might be best fit. I should have used a pencil, but I'm going to see how this one looks. Okay, this is this much below, touching, a little bit below, touching, tiny bit below. I would say my real line is going to be somewhere in between there. Okay, I think I'm about ready to draw my final line. Again, if I were to use a pencil, that would make it a lot easier. And I understand that we're not using stats here. We're just using plain old eyeball method. All right, so what do you think? Could everybody have what they think? Do you consider that to be a biased line? What I'd like you to do is take about 30 seconds, trade your graph with the person next to you, and then ask them their unbiased opinion about your line being biased or not. I think they could do that. So what do you think about my line? Is it biased or is it best fit? Is it a biased line or is it best fit? And if it's not super obvious, it's probably pretty close. All right, what do you think? Yes.
Do you care if we go off the axis?
No, that's all right.
You want us to go off either side?
Yeah, you can. Okay, can I have your attention now? We can start again. Now, let's assume, without using stats, that we can, and one of my goals is, could you draw a best fit line eyeballing it that was close to the one you get with stats? I mean, close. And if it is, that's not bad. So what I'm going to do here is I want to show you what we're doing here. See, I took the time to get my equipment out, and I got this information here, but how much information is available to me? Would you say it was 6 pieces of information or 12? Because every one of these dots has an X and a Y. You think it's 6 pieces or 12? And what do you think? How much information is available to me now?
Infinitely big.
12 or infinite? And the answer is infinite, because the reason I have somebody who's going to help me with this a little bit. Yeah, we're doing this thing every year. We know this thing, best fit line, and I want you to help me with this. You mind? Why did I even do this experiment? You told me to do it, but I forgot. It says that is why you fail. But I'm trying to do the best I can. Why did I even put the dots on there? In math class, I put the dots on there, and the line goes through every dot, but it doesn't even go through every dot here. Oh, you do not seek the dots. What do you mean? Yeah, I did the experiment. I wanted the dots, didn't I? No, you seek the line. And so what you need to remember is that the reason I did the experiment was not for the dots. It wasn't for the data points. I needed the data points, but my goal was not the data points. It was what? The line. And the line is the relationship between the variables. That's what I wanted. As a matter of fact, what we're doing here, and we'll talk more about this tomorrow, is in a controlled experiment, there are only 2 variables that are allowed to change. One of them is the independent variable, and one's the dependent. And what I have to be careful about is, what do I do to all the other variables? In this experiment, I didn't go around changing my graduated cylinder halfway between it. I wanted that variable to be held constant. So when you say a controlled experiment, you control variables by holding them constant. Get that? A control variable does not change. But the independent dependent variable, they did change. That's why they're called variables. And so what I'm doing here, I'm trying to find out if there's a relationship that exists between these 2 variables. And you can look at it and you say, you know what? Not only does it exist, what's this? Not only does the relationship exist, but we already know it's linear, don't we? We know there's a linear relationship that exists. Is that correct? It's linear. Okay. So now what we want to do is we want to go a little further by analyzing this thing by finding the slope. Now, what we're going to do here is a little bit different than you do in math class. This is not different. Slope is rise over run. And you say, well, how do you find out how much a line rises? Well, you want to find out how much it changed in the y-axis. That's a delta y. Delta y is change in the y divided by how much it changed in the x-axis. And I didn't even make up the definition of slope. Somebody else did. Slope is like steepness, isn't it? And so this guy has a certain steepness, doesn't it? Okay, now, the math teacher would have done this. They'd say, well, how do you find delta y? You say, well, you take the second y value and you subtract the first. And then you divide that by x2 minus x1. And I know you guys are more sophisticated in math because you're in stats, but almost every year I still have people that think a little tiny 2 means squared. And I don't know if anybody in here, probably not, but a little tiny 2 written down low is not squared. But some of you see that, you think it means squared. And if it's written as a superscript, it is an exponent. But if it's written as a subscript, it's just a name tag. And one thing they do in physics all the time, and you see it on TV, you said, oh, who can understand that? You can. And they love doing this stuff like this. Ready? They do like this. The force of attraction is equal to the mass of the Earth times the mass of the moon. And that already looks complicated, doesn't it? But all they're doing is putting, instead of numbers, math people like to use numbers as name tags, and physics people like to put letters as name tags. You get it? The acceleration equals V2 minus V1. That's the way the math teacher do it. The physics people would say VF minus VI. And what that means is final velocity minus initial velocity. Get that? And yeah, it makes it look like, ooh, physics. But they're just little name tags, aren't they? And that's what these are. They're just little name tags. Now, here's where I'm going to do something different than they do in math class, okay? When I grade your graphing skills, I'm going to ask you to pick 2 points in this line to find the slope with. Now, to reduce my error a little bit, I don't want the points to be really close to each other. Get that? So we're going to try to spread them out. Maybe one down in here, maybe one up in here. Now, I have an infinite amount of information. I can pick any dot I want. Do not pick dots off of the data table. You say, that's the way you do it in math. You're right. In math class, you would actually use this to find your slope, wouldn't you? And you have to get out of that habit because those dots are always on the line, but not in an experiment. In an experiment, you say, well, I'm going to use this dot right here. And that dot is not even on the line. You can't find the slope of the line by using a data point that's not on the line. Is that right? So you had to pick 2 points that are not data points. And so what I do is I'm going to be nice to myself. I'm going to go through here, and I notice that, ooh, look at here, right there. I noticed that, and I'm going to have you put these little plus signs. Now, the plus sign is really like a crosshair. I don't know if you ever had a rifle with a scope. You ever done that? Crosshair. Okay. I happen to know that my line went right through that crosshair, and that's going to make it really easy for me to write the x and the y value. It's 5 in the x direction, and it's 4 in the y direction. Okay? Then I go over here, and I'm going to pick one near the other end. And now I don't want you to write that down because I want you to do your own line. Okay, don't write my numbers down. No. Where's no? Okay, here's one. This one is 13.5. 13.5 and 11. Okay, so now, again, when I'm grading graphing skills, I am going to ask you to write down the coordinates here. So when I check your work, I'll know how you did it. So let's go ahead and do the slope. And y2 is 11 minus 4. But here's something they don't do in math class. It's not 11 minus 4. It's 11 grams minus 4 grams. They don't do that in math. And a light bulb might come on. Maybe a light bulb will come on somewhere in the next couple of minutes. You'll say, oh, I get it. Anyway, so the slope is, and be careful about this. I know you guys are like a little bit better than the last class as far as math, but they always give coordinates x first and y. But remember, the slope is y over x. Can you remember that? That's the biggest mistake people make on slope. And now my x2 is 13.5 minus 5. And that's in milliliters. All right, so I need somebody who has a calculator. Avery, you ready? Ready? Give me 7 divided by 8.5. 0.8 what? 8235. Okay. And it's in grams per milliliter. Okay. What I'd like you to do is each person, I want you to find the slope of your line, okay? And we'll go around the
You
room.
can represent it as a fraction. shouldn't you?
No. Okay, that's another thing we do different. Okay, excellent. Thank you for saying that. In math, they want you to put something like 9/16 as the slope. I do not ever want you to do that here, okay? I want them to be decimal numbers, okay? So it could be 1.55 or 0.222, but don't leave fractions in your slope. Yes?
How many sig figs?
Say it again. Ask them what the reasoning for having fractions, and I'll tell you why. Because they want to be in a world of exact numbers. And what they're going to say is, you better not put 0.333 because it's really 0.33 to infinity, isn't it? So they don't want you to put 0.33. They want you to put 1/3. I get it. 1/3 goes to infinity. 0.333 doesn't. I get it. In a world of measured numbers anyway, you don't go to infinity. Your measured numbers don't go into infinity. And so what's going to happen is, I'm going to have you put not fractions because we're going to eventually put it into an equation. We're going to eventually put it into an equation. So I don't want you to use fractions, just like they could say to you, I don't want fractions. And you say, okay. And that's what I'm doing. So I understand why they want fractions, because they go to infinity, some of them, and I get it. Yes?
How many sig figs do you have to do?
Even though eventually the measurements on the experiment will dictate that, you could use 3 for right now. I could actually go back to the data table, and I notice that my weakest point is 2. So I know I have only 2 data points in some of these, 2 sig figs. So I guess I'd have to say, actually 2. In this case, 2. So I put 0.882 probably. Anyway, I'd like to go around the room, and I want you to tell me what you got for your slope. All right, and please don't do the peer pressure thing where, you know, your number is completely different. If it is completely different, it might be the only one right. So, all right, let's start here. What do you have for your slope?
I have 8.33.
8 point what?
Or sorry, 0.833.
0, 0? Okay, next. Becca. Say it again. 0.9. Okay, next. 0.857. Next.
0.857.
Point what?
0.857.
Really? Okay. Avery.
0.889.
889. Next.
0.86.
8 what? Everybody, wait. I can't hear. Wait.
0.86.
Next.
0.869.
Next.
0.8.
Next.
0.846.
Next.
0.9333.
Next.
0.875.
Next.
0.857.
857. The dyslexia get in there. Next.
0.75.
Point what?
75.
All right, next.
0.833.
833. Next.
0.868.
868.
0.857.
Okay. Now, the only thing I want you to see here is that we're all in sort of the same ballpark, but this is using eyeball method, isn't it? Now I want you to get your calculators out, and I want you to do a linear regression on this go ahead and take about a minute or so. And remember how you do the list and do a linear regression and see what statistics says the slope is going to be. And then we're going to see if you happen to, let's say the answer is like really 0.9. Then whoever gave me 0.9, wow, your eyeball method is really good.
That was me.
Okay, and what if the answer is 0.7? Then we all made a pretty big mistake.
Except for the person who said 0.75.
Oh, that's right.
Oh, Clay, you got it.
For
Okay.
some reason, I'm feeling a strong gravitation towards 0.865.
What is it?
41.
0.8 what?
0.86539.
Okay.
Look at that, I got that exactly right.
All right, is everybody getting that on linear regression? Is everybody getting 0.865? What do you think?
Yeah.
Yes.
Wait, what?
All right, if you're getting that with linear regression, then it says using all the statistical calculations that the best fit line should have a slope of 0.865. And so what's interesting is, I bet if we took the average of these, it'd be pretty close, I bet. Now, I had somebody last period, they had like they had 1.27, and I almost immediately knew what they did, and you do too, don't you? What did they do?
Oh, they did rise up and run. Or they didn't run over rise.
What's the reciprocal? What is 1 divided by 1.27? And it came out to be 0.88. So anyway, that's a common thing that people do. They switch the x and y's.
Yep.
And see that?
Yep.
Okay.
That's what I got.
I just want to point out all these things here.
No,
Okay.
great.
Questions so far on this?
It is.
Now, what we're going to do is, and again, maybe the light bulb didn't come on yet, but why did the person want to do this experiment? Just to say, hey, I can show you that I know how to find the slope. I mean, scientists will never do that. If they find the slope of a line, it's because it means something. There's some meaning to them. And in this case, the slope came out to be around 0.865 grams per milliliter. Now, what do you think that means? What does it mean that the slope of this line is 0.865 grams per milliliter? What do you think? Yes? It is. And it just happens to be that somebody said, I'm going to make a vocabulary word for science. And the science says, not what is your mass, not what is your volume, but I'm going to give a name for the amount of mass per volume, and they called it density. And density always has two units in it. It has a mass unit and a volume unit. And most of the time you'll see grams per cubic centimeter, but a milliliter is a cubic centimeter, isn't it? Isn't that right? So that's the same thing. And so what I think is interesting, and if the light bulb didn't come on, well, first of all, you have to be plugged in. But the next thing is, here we go. See if the light bulb comes on. Why is the slope of this line density? Because density equals mass over volume. But slope equals whatever's on the y-axis divided by what's on the x-axis. So why did the person want volume to be their independent variable? Because they wanted to find the slope, which would have been the density. In this case, the slope is whatever's on the y-axis divided by what's on the x, and mass divided by volume is density. You could have done this experiment the other way, and you would have gotten another ratio, but it wouldn't have been called density. You get that? So it looks like this person was trying to find the best number possible for the density of this liquid. What do you think? That's pretty neat stuff. I remember doing graphs all over the place in math, and I did some graphs in science, but I clearly remember the day I said, what? The slope actually means something in science? And it did. And you also know things like this. You know that every straight line can be represented by y equals mx plus b. Is that correct? Now, we're not going to use y and x because we're at a real experiment. What is on the y-axis? Mass. Mass equals. And what's the little m? In this case, it's 0.865 grams per milliliter times x. What's on the x-axis? Volume. And now, it's just a coincidence, and I hate to tell you, that your graph may not go through 0, 0. when you guys do your own experiments, have I seen groups that were so careful and they measure so well and they zeroed out everything? Have I seen some people's graphs go through 0, 0? I have. But if they don't go through 0, 0, that's okay. Who did the linear regression? Did they happen to have a y-intercept on that? Do you happen to know? Can you bring that back up? I made up these data points. I made them up. What was it? Oh, negative 0.5? Okay, interesting. Now, this one didn't quite go through 0, 0, did it? And for a scientist, it means something. I tried to zero out everything, but somehow it still statistically shows me there's a little bit of error here somewhere. And if they could ever get this thing close to 0, 0, there's some things you can't get rid of, and they know that. All right, let's go back down in the paper, and let's read back on this page here. Now I'm going to finish this today, so I can go. Like I said, go a little bit faster with you guys, but I do want you to read all this. You draw a best fit line. Every measured number has error. The goal of the experiment is not the dots. That's what Yoda said. You seek the line. The line is the relationship between the two variables. A straight line shows a linear relationship. A curved line is called a nonlinear relationship. A smooth curved line cannot go dot to dot and be best fit. So you can actually do a best fit curved line. You may want to try to determine whether in each specific experiment the best fit line will go through 0, 0. You cannot assume that will go through 0, 0. And then we just tried to talk about how to draw that. Let's go to the next one. 2 vocabulary words. You guys are probably pretty deep into stats, aren't you? Have you had interpolation, extrapolation?
Yep.
Okay, good.
Oh, yeah.
I remember the first time I heard those words, I didn't know what they meant, but I eventually figured out a memory trick that if you gather data from a graph and you stay within the actual data point, within it, then it's interpolating data. And if you were to go outside your data points, then you're called extrapolating data. Extrapolating data is useful to lots of people, but there is a danger, isn't there? The danger says if that trend doesn't continue, then your extrapolated data is no good, isn't it? So let's go down here. Here's a question. What would be the mass of 8 milliliters of this liquid? And if you look at your data table, you say, well, how am I supposed to know that? I didn't do the 8 milliliters. You say, well, yeah, you forgot. How much information do you have available to you now? Infinite. So now let's go find 8 milliliters. 5, 6, 7, 8. I go up here till I hit the line, and then I go across, and it looks like it's going to be right about here. Okay? So I have interpolated the data. 8 milliliters would have a mass, my graph says somewhere around maybe 6.7, 6.8. What did you guys get? 6.8? Okay. I'll draw that in there. So I interpolated. It's going to be somewhere around 6.7, 6.8. Look at the next question. It says, what volume of this liquid would have a mass of 20 grams? Let's get back to the graph. Now, there are two things I could do. 20 grams are up here, and my graph doesn't go there. Two things I can do. I could extend the line. If my graph paper is bigger, I could extend the line and see where it hits, and then read straight down. But what else could I do? Okay, so let's put it in the equation. Y equals mx plus b. And you said the plus b was what, negative 0.5? Okay, so let's do that. Let's put 20 in for the mass. So 20 equals blah, 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 blah. So we add this to both sides. 20.5 equals, now divide, and if somebody give me a hit on the calculator, please. 20.5 divided by 0.865. 20.5 divided by 0.865. Anybody have that? 20.5 divided by 0.865. Anybody hit? Do you have that, Mason? 20.5 divided by 0.865. Anybody?
23.7.
One more time.
23.7.
Okay, good, thank you. So I'm gonna go back and I can now use this equation to say that it was about 23.75? No, 23 point what? 7? Okay, all right, sorry. All right, so then what we did is, we know that there's interpolating data, there's extrapolating data. Yes?
Why wouldn't you just plug 20 in for x in the equation? Why would you set it equal?
Why would I put in an equation?
No, why wouldn't you just plug 20 for x in the equation? Why would
Okay,
you-
I think it said, let me look here. It says, what volume would have a mass of 20 grams? So I had to put the 20 grams in, I had to put 20 grams in for M, for mass. And then I added 0.5 to both sides and then divided by 0.865, like that. Does everybody get this? All right, now what I'm gonna do is spend just a little bit of time here with this. And by the way, you can fill this out. I'm not grading it, but you can read this and some of the stuff we just did in class. That's how you find the slope. And what I want to know, and again, I know you guys are more advanced, but I can't help by thinking there has to be some of you in here that you still might not catch on to this other word, this other thing I'm going to do here. Math teachers are known for saying this, and yet some students tell me they've never heard it, and I find that hard to believe. How many slopes does a straight line have? And if all of you in your brain right now, if all of you are not saying immediately 1, then there's some miss here. Because math teachers are famous for telling you, well, straight lines only have 1 slope. Now, I'll tell you, this bothered me, and I will spend a lot of time this year talking about ratios. Your mind doesn't really like ratios like you think they do. The ratios are a tough thing for humans, and yet some of the best things in science are ratios. And so when you get to some of this stuff in physics, and you'll find out, wow, that's good stuff, it's probably a ratio. So let's take a look down here. Here's a line. What happened? Oh, did I say something?
Would this be a ratio if it's good stuff?
Ratio is good stuff? Yeah.
Unless they're good stuff.
I must have said something. I'll go watch the tape. No. I don't know what I said. Anyway, so what happened is, I remember that the math teacher said the straight line has only 1 slope, but I don't remember ever saying why. I didn't understand why. I just had to memorize it. Get that? And so let's take a look here. If I'm down here on this part of the line, and then I'm here, which one has the greater slope? And you're supposed to learn to say they all have the same slope. But it should bother your brain, because your brain says the x's keep getting bigger and the y's keep getting bigger. And that's that idea of ratios. And so we can take a little number like, let's just pick one, 2 and 0.5. Okay, so 2 and 0.5. I just made up 2 numbers, okay? And then as you go up the line, maybe it's going to come like this, 4 and 1. And you keep going up the line, and then the next one is 10 and 5. 2.5. And so what you notice is that the y's keep getting bigger, and the x's keep getting bigger, and they call that proportionally. They're getting bigger proportionally. And so what happens is, if this gets bigger and this gets bigger by the same rate, there's something that doesn't get bigger, and that's the ratio. The ratio will not get bigger. What's this come out to be? 4, 4, 4. So when they say the slope, a straight line has only 1 slope, it's because, not because the x's don't get bigger, they do. The y's do get bigger, but the ratio of y to x does not get bigger. And so here's another thing they might have taught you in middle school. What's the density of a piece of steel? It's around, I'll just round up, 8 grams per cubic centimeter. All right, cut the piece of steel exactly in half. What is the density of half of that bar of steel? And everything in your mind from elementary on says 4, doesn't it? But what is the density of half of that bar of steel? And some science teacher probably said, it's the same. Oh, I'm supposed to say 8. I don't know why, but I'm supposed to say 8. Well, now maybe you know. Maybe you know that you could have a large mass and a large volume, and that ratio come out to be 8. What if you cut it in half? You cut the mass in half and the volume in half. What happens to the ratio? It doesn't get cut in half. It stays constant. And so what happens is, this is a constant in science. The slope of a straight line is a constant. Okay, so let's go back over here. Excuse me. Now, look at this experiment here. See if you can tell me what is the why did the experimenter do this experiment? What was their goal? And what did they come out with? So take a look at this experiment here and tell me what you think the slope means and why they did the experiment. What were they looking for? What were they looking for? What do you think? Yes?
Speed.
Say it again?
Speed.
Now she says speed, and some of you are saying, how in the world did you get that? Well, remember, slope is whatever's on the y-axis divided by what's on the x-axis. So the slope was going to come out to be miles per hour. And just like somebody said the ratio of mass over volume should be called density, somebody else said, I want to make a word that talks about the ratio of distance over time. And I'm going to call it speed. I'll tell you, the first time I heard this, and we'll have a whole chapter on this kind of stuff with in physics, this graph is a graph of constant speed. I remember the first time I heard that, that bothered me because I saw a line that was going up. The line was going up, but what did it represent? Constant speed. The x's kept going up, the y's kept going up, but you know what didn't go up? The ratio, and the slope of that line is the ratio, isn't it? That's a graph of constant speed. Look at this right here. What are they doing here? This is going to be grams per penny. See that? Why are you doing this experiment? Nobody has a name for that, but maybe the person said, I have a bunch of pennies, I don't want to count them, and I want to know the best number I can come up with for the mass of 1 penny. Grams per penny, that'll come out to be the best average mass for 1 penny. And now I can tell my machine, put it on my program, put all those pennies in there and weigh them. And the computer says, you gave me $15.88 in pennies. But if I had a bad number for the average mass of a penny, I'd be giving out the wrong amount of money. On the homework assignment, it doesn't take very long, about half an hour. Do your best work. You might think about using a pencil. Okay, thank you very much.